Virtual machines, containers, hypervisors, cloud computing. These terms get thrown around constantly in tech discussions, but do you really understand what's happening behind the scenes when someone spins up a Docker container or launches an EC2 instance? Most people think they do, but the reality is far more complex and fascinating than you might imagine. Here's the thing about virtualization technology. It's not just one thing. It's an entire ecosystem of interconnected systems that have completely revolutionized how we think about computing resources. And if you're working in tech today without understanding these fundamentals, you're missing critical pieces of the puzzle that could transform how you approach every project. I've spent the last decade working with virtualization technologies in production environments, from managing bare metal hypervisors to orchestrating thousands of containers across multiple cloud regions. What I've learned is that most explanations either oversimplify the concepts or get lost in technical jargon that makes your eyes glaze over. Today, I'm going to walk you through every major virtualization technology in a way that actually makes sense. By the end of this video, you'll understand the core differences between Type 1 and Type 2 hypervisors, why containers aren't actually virtual machines, what makes serverless computing so revolutionary, and how technologies like Kubernetes and Docker work together to power the modern internet. But before we dive into the technical details, let me tell you why this matters more than you think. Every single application you use today, from Netflix to your banking app to the website you're watching this video on, relies on virtualization technology in some form. Understanding these concepts isn't just academic knowledge. It's the foundation that determines whether you can architect scalable systems, optimize costs, or even land that next tech job. Traditional computing used to be simple. You had one computer, one operating system, and you ran your applications directly on that hardware. But this approach had massive limitations. If your application crashed, it could take down the entire system. If you needed more processing power, you had to buy entirely new hardware. And if you wanted to run multiple applications that required different operating system configurations, you were out of luck. Virtual machines changed everything by introducing a layer of abstraction between the hardware and the operating system. Think of it like having multiple computers running inside a single physical machine, each completely isolated from the others. But how does this actually work under the hood? The magic happens through something called a hypervisor, which is essentially a thin layer of software that sits directly on top of the physical hardware. The hypervisor's job is to manage and allocate system resources like CPU, memory, storage, and network connectivity to multiple virtual machines running simultaneously. Each virtual machine thinks it has dedicated access to physical hardware, but in reality, the hypervisor is constantly juggling resources between them. There are two fundamental types of hypervisors, and understanding the difference is crucial for making the right architectural decisions. Type 1 hypervisors, also called bare metal hypervisors, run directly on the physical hardware without needing a host operating system. Examples include VMware vSphere, Microsoft Hyper-V, and Citrix XN Server. These are what you'll find in enterprise data centers and cloud providers because they offer the best performance and security isolation. Type 2 hypervisors run on top of an existing operating system, treating the hypervisor itself as just another application. VMware Workstation, Oracle VirtualBox, and Parallels Desktop fall into this category. They're perfect for development work or running a few virtual machines on your laptop, but they introduce additional overhead because you're essentially running an operating system on top of another operating system. The performance implications are significant. With Type 1 hypervisors, virtual machines can achieve near-native performance because there's minimal overhead between the guest operating system and the physical hardware. Type 2 hypervisors sacrifice some performance for convenience and ease of setup, but virtual machines, as powerful as they are, still have limitations that became apparent as computing demands grew. Each virtual machine requires its own complete operating system, which means you're duplicating a lot of system resources. If you want to run 10 web applications, you might need 10 separate Linux installations, each consuming gigabytes of memory and storage just for the operating system itself. This is where container technology fundamentally changed the game. Containers provide process isolation without the overhead of running multiple operating systems. Instead of virtualizing the entire hardware stack like virtual machines do, containers virtualize at the operating system level, sharing the host kernel while maintaining complete isolation between applications. The most famous container technology is Docker, but it's important to understand that Docker isn't the only container technology, and containers existed long before Docker made them popular. Linux has had container capabilities through technologies like LXC for years. What Docker did was create a standardized way to package, distribute, and run containers that made the technology accessible to developers everywhere. Here's what makes containers so revolutionary. A container includes everything needed to run an application: the code, runtime libraries, system tools, and dependencies, but it shares the host operating system kernel. This means you can run dozens or even hundreds of containers on a single machine that might only support a handful of virtual machines. The startup time difference is dramatic. While a virtual machine might take minutes to boot because it needs to load an entire operating system, a container can start in seconds or even milliseconds because it's just starting application processes on an already running kernel. But containers introduce their own complexity, especially when you're running them at scale. Managing networking between containers, handling persistent storage, ensuring high availability, and coordinating deployments across multiple hosts becomes increasingly challenging as your container footprint grows. This complexity led to the development of container orchestration platforms, with Kubernetes emerging as the clear winner in this space. Kubernetes doesn't replace containers, it manages them. Think of Kubernetes as the conductor of an orchestra, coordinating hundreds or thousands of containers across multiple machines to create a cohesive application platform. Kubernetes handles service discovery, load balancing, automatic scaling, rolling deployments, and failure recovery. When a container crashes, Kubernetes automatically restarts it. When traffic increases, Kubernetes can automatically spin up additional container instances. When you need to deploy a new version of your application, Kubernetes can gradually roll it out while maintaining zero downtime. The abstraction layers keep building. Cloud providers took these concepts and created even higher-level abstractions that remove infrastructure management entirely from the developer's concern. Infrastructure as a Service, or IaaS, represents the first major cloud abstraction layer. With IaaS platforms like Amazon EC2, Google Compute Engine, or Microsoft Azure Virtual Machines, you're essentially renting virtual machines from massive data centers without having to purchase, configure, or maintain the underlying physical hardware. The cloud provider handles everything from power and cooling to network connectivity and hardware failures, while you get root access to virtual machines that behave exactly like dedicated servers. The economics are compelling. Instead of spending hundreds of thousands of dollars on servers that might sit idle during low traffic periods, you pay only for the compute resources you actually use. Need more processing power during a traffic spike? Spin up additional instances in minutes. Traffic dies down, terminate the extra instances and stop paying for them. But ES still requires significant operational overhead. You're responsible for operating system patches, security configurations, monitoring, backup strategies, and all the traditional system administration tasks. This led to Platform as a Service, or PaaS, which abstracts away even more of the infrastructure complexity. PaaS platforms like Heroku, Google App Engine, or AWS Elastic Beanstalk let you deploy applications without worrying about the underlying servers at all. You write your code, specify your dependencies, and the platform handles everything else. Scaling, load balancing, operating system maintenance, and security patches all happen automatically behind the scenes. The developer experience is dramatically simplified. Instead of spending time configuring web servers, databases, and monitoring systems, developers can focus entirely on writing application code. But this convenience comes with trade-offs. You're locked into the platform's supported languages and frameworks, and you have less control over the underlying infrastructure configuration. The next evolution pushed abstraction even further with serverless computing, though the name is somewhat misleading because servers are definitely still involved. What serverless really means is that the concept of servers becomes completely invisible to developers. You write individual functions that respond to specific events, and the cloud provider handles everything else. AWS Lambda pioneered this approach, followed by Google Cloud Functions and Azure Functions. With serverless, you don't even think about scaling. You upload your function code, define what events should trigger it, and the platform automatically runs your code whenever those events occur, scaling from 0 to thousands of concurrent executions instantly. The billing model is equally revolutionary. Instead of paying for server uptime, you pay only for actual execution time, measured in milliseconds. If your function isn't running, you're not paying anything. This makes serverless incredibly cost-effective for workloads with sporadic or unpredictable traffic patterns. But serverless introduces its own constraints. Functions have execution time limits, memory restrictions, and cold start latency when they haven't been used recently. Complex applications often require combining multiple functions with careful orchestration, and debugging distributed serverless applications can be challenging. The abstraction doesn't stop there. Modern application architectures are moving toward microservices, where large applications are broken down into dozens or hundreds of small, independent services that communicate over network APIs. Each microservice can use different programming languages, databases, and deployment strategies, but coordinating all these moving pieces requires sophisticated tooling. Service mesh technologies like Istio and Linkerd provide infrastructure for microservice communication, handling concerns like service discovery, load balancing, encryption, and observability without requiring changes to application code. These tools create a dedicated network layer for service-to-service communication, making complex distributed systems more manageable and secure. Edge computing represents another significant shift in how we think about virtualization and distributed systems. Instead of centralizing all computation in massive data centers, edge computing pushes processing power closer to end users through networks of smaller, geographically distributed computing nodes. Content delivery networks like Cloudflare and AWS CloudFront started as simple caching layers, but they've evolved into full computing platforms capable of running application logic at the network edge. This reduces latency for end users and enables new types of applications that require real-time responsiveness. The convergence of these technologies creates fascinating possibilities. You might have a mobile application that triggers serverless functions running at edge locations, which coordinate with microservices running in Kubernetes clusters, backed by databases running on traditional virtual machines, all orchestrated through cloud-native tooling that abstracts away the underlying complexity. Understanding when to use each technology becomes critical for building effective systems. Containers excel for applications that need consistent environments across development and production. Serverless works brilliantly for event-driven workloads with variable traffic. Traditional virtual machines still make sense for legacy applications or workloads requiring specific operating system configurations. The landscape continues evolving rapidly. WebAssembly is enabling new approaches to sandboxed execution that could challenge traditional container models. Confidential computing technologies are making it possible to run sensitive workloads in untrusted environments through hardware-level encryption. Quantum computing, while still experimental, promises to revolutionize certain types of computational problems. These aren't just academic concepts. Every major technology company is betting their future on these virtualization technologies. Netflix runs entirely on AWS infrastructure using a combination of containers and serverless functions. Spotify manages millions of users through Kubernetes orchestrated microservices. Even traditional enterprises are rapidly modernizing their infrastructure using cloud-native approaches. Understanding virtualization technologies isn't just about keeping up with industry trends. It's about fundamentally changing how you think about building and scaling systems. From bare metal hypervisors to serverless functions, each layer of abstraction solves specific problems while introducing new possibilities. The next time you deploy an application or architect a system, you'll have the knowledge to choose the right virtualization approach for your specific needs. And that makes all the difference.